All right, trust you did well on your quiz, and we'll take a look at those next time. For now, if you would, turn in your textbooks to page 517. Page 517. And I want to talk to you about something that you see there at the very top of page 517, and that's the term like radicals. The term I often will use is the term similar radicals. Like radicals, similar radicals, mark, highlight, underline, circle, star, whatever you have to do, that first sentence of the page. Like radicals are radicals that have, say it with me class, the same index and the same radicand. What two things have to be the same? Index and radicand. Now think about it. How many parts are there to a radical? 3. There's the radical sign, there's the index, and there's the radicand, right? Well, all radical symbols are drawn the same. So if they have the same index and the same radicand, they are exactly identical. But you know what doesn't have to be the same is whatever's in front. For instance, 5 times the cube root of x squared and 17 times the cube root of x squared. These are radical terms. They're terms that have radicals in them, right? But the radicals themselves, index, symbol, radicand, they're exactly the same. These would be considered similar radical terms. Does that make sense? Kind of like a 5x squared y to the 7th and a 17x squared y to the 7th. To be like terms, everything after the numbers have to be identical, right? Same thing here. Everything after the coefficients would have to be identical for these to be considered similar radicals. Make sense? Look at page 517. They got some different examples, like square root of 5 and square root of 5. Well, those have the same indexes. They also have the same radicands. In fact, they're literally the exact same thing. But square root of 3 and square root of 6. Well, those have the same indexes, but not the same radicand. So they could be multiplied, same index, but they're not similar. They're not like radicals. 2 square root of 2 and 3 square root of 2. Yeah, same index, same radicand. 5 square root of 2 and 5 cube root of 2. No, the indexes are different. They're different kinds of roots. 2 times the cube root of 7 and 4 times the cube root of 7. Yeah, same index, same radicand. 8 times the cube root of 4 and 8 times the cube root of 9. Same index, but not the same radicand. Do we get the idea of similar radicals?
Why does it say no on the...
Well, no would mean it doesn't have the same radicands or doesn't have the same indexes.
I was looking at the first part of it.
Gotcha. So yeah, I was kind of doing a side-by-side look. Okay, so, but here's the deal. In order to figure out whether or not radicals are similar, they have to be reduced first. And I don't know if they don't have that actually written quite in those terms. So I want you to write that in the side margin of your book on page 517. You must reduce radicals first to determine if they are similar. You must reduce radicals first to figure out if they are similar. For instance, the square root of 12 and the square root of 75. On the surface, you must reduce radicals to tell if they are similar. Look at these. Square root of 12, square root of 75. At a cursory glance, we look at it and say, no, of course they're not similar. But watch. This can factor into 4 times 3. That's 2 times the square root of 3, right? This can factor into 25 times 3. That's 5 times the square root of 3. So, class, are they similar? They are. They don't look like it this way, but that's not their simplified form yet. When they're simplified down, oh, yes, they are similar. Look at the examples. They're on page 517. The square root of 3 and the square root of 20. Well, before you rush to judgment, simplify that square root of 20. Well, when they do, it becomes 2 times the square root of 5. Is that the same kind of radical as the square root of 3? Are those like radicals? No. One's the square root of a 3, the other's the square root of a 5. Those ain't the same. Look at the next ones. The square root of 12x and the square root of 147x. Well, look at what they did. They factored 4 times 3 times x to get 2 times the square root of 3x. They had 3 times 49. Now, they wrote 7 squared. I would write 49. 3 times 49 times x. They took the square root of 49 to get 7 times the square root of 3x. And lo and behold, they're similar radicals, aren't they? So to determine whether or not radicals are similar, of course, we want to reduce them first. Now, The reason it's important to get similar radicals is because only like radicals can be added. You see that statement in bold. Circle it, star it, highlight it, do something to mark it. Only like radicals, only similar radicals can be added together. Look at that example there on page 517, that little blue box. And this is exactly how I ordinarily would teach this. Just as if you wanted to take a 3x plus 4x, you would add just the numerical coefficients to get 7, and you just keep the same x they've had all along. You have 3 x's plus 4 more x's equals 7 x's, right? The same thing would be true if this was like a 3 times the square root of 5 plus 4 times the square root of 5. Well, if I have 3 square roots of 5, and then I add 4 more square roots of 5, I have 7 square roots of 5. Does that make sense? I don't add the radicands together. It's this many square roots of 5 plus that many square roots of 5 equals that many square roots of 5. Make sense? So if I were to add 5 times the cube root of x squared plus 17 times the cube root of x squared, what would I get here, Josh?
22 times the cube root of x squared.
Right, 22 times the cube root of x squared. You just add the numbers, the coefficients, but you leave the radicals as they were. Turn the page, page 518. Turn the page, page 518. Notice the example problems that you see here on page 518. Notice 3 times the square root of 2, the second radical there in the yellow box. It looks great, 3 times the square root of 2, but look at the square root of 50. That's a really big radicand, isn't it? That can probably factor down, and you notice it does. 25 times 2, they take out the square root of the 25 to get 5 times the square root of 2. Well, now, 5 times the square root of 2, 3 times the square root of 2, those are like, those are similar. So they added them to get 8 times the square root of 2. Do we understand the first example? Look at the next example, the cube root of 24x and a cube root of 81x. Well, we have to simplify. Well, 24 factors at 8 times 3. Take the cube root of 8 to get 2. 2 times the cube root of 3x. For the 81, factor that into 27 times 3. Now, they show 3 cubed times 3. That's fine. 27 times 3, the cube root of 27 is 3. 3 times the cube root of 3x. 2 times the cube root of 3x plus 3 times the cube root of 3x. 5 times the cube root of 3x. Do we understand the second example? Are there any questions on the example problems that you're looking at? Do you follow what they did? Do we need to see that on the chalkboard for either of them? You sure? All right, well, let's take a look at some of these together. Look at number 1 in your textbook. Are these radicals like radicals, class, in number 1?
Yes.
They're in fact identical. Now be careful. What would you get if you added the square root of 13 plus the square root of 13?
2 times the square root of 13.
Good. Not the square root of 26. 1 square root of 13 plus 1 square root of 13 equals 2 times the square root of 13. Great job, Lana. Number 2. Are those like radicals, Josh?
Yes.
Yes. Okay, so what do you get when you add 2 times the cube root of 5 plus 3 times the cube root of 5?
5 times the cube root of 5.
5 times the cube root of 5. Very good. Number 3. Lana, are those like radicals?
No.
No. They have the same indices, the same indexes, but they don't have the same radicands. So although you could multiply to get square root of 77, you can't add them. So just circle the problem. The problem is its own answer. Just as 3x plus 5y equals 3x plus 5y, because you can't do anything with it. So the square root of 7 plus the square root of 11 equals the square root of 7 plus the square root of 11. What about number 4? Are those like radicals, Josh?
No.
On number 4?
Wait.
Do you have the same indexes?
Yes.
And the same radicand?
Yes.
And are they similar?
Yes.
Yep.
I was looking at the signs, isn't it?
Now the signs are different. What would you get, Josh, if you added a negative 1 squared root of 21 and a positive 1 squared root of 21? 0 times the square root of 21, but notice I said times, right? 0 times anything equals 0. So your answer is 0. They're inverses. They cancel. Just as a positive 3x, negative 3x, we would say cancel. So a negative square root of 21, positive square root of 21, cancel each other out. Make sense? Same type of thing. How about the next one, Lana? Are those similar radicals?
No.
No, because they don't have the same indexes. They're really close, but nope, so you just circle number 5. That is its own answer. Number 6, Joshua, similar radicals?
Yes. No.
Nope, they don't have the same radicand, so can you add them?
You can't add them.
Nope, so what's your answer on number 6?
That.
Circle the problem is the answer. Number 7, what do you get when you add those together, class?
2 times the square root of 14.
2 times the square root of 14. How about number 8? What do you get, Lana?
5 times the square root of 5.
5 times the square root of 5. Very good. Number 9. Careful here, Josh. What do you get when you add these?
-4 times the cube root of 12.
-4 times the cube root of 12. Fantastic job. Make pretty good sense how to add similar radicals together. Any questions on what makes radicals similar or not? Any questions at all on what we talked about today? All right, your homework for this evening has really not anything to do with radicals. Homework is to do page 519, page 519, the review, numbers 25 to 33. Page 519, numbers 25 to 33. It's in the review section. Take a look at that as well as your quizzes in our next lesson, and then we'll practice some more with adding similar radicals together. Have a wonderful rest of your day.